Good morning, everyone. For today's tutorial, I'm going to explain the Euler formula on T-beams. Okay, so for example, we have here a T section. We have here a T section of a column, which is 240 by 120. So in other words, you have here this is 240 millimeters, and then you have your 120. From here going here is 120 millimeters. So in other words, you also have here 20 millimeters. Okay, that means from here you have 100. Okay, it is also known to be 20 in this side. Okay, so by the Euler's formula, we know that P is equal to E pi E I, okay, pi squared EI over the equivalent length. Now for this type of column, both ends are fixed. So our equivalent length is just equal to L over 2. Okay, so in this case, our length is 6 meters long. So 6 divided 2. This means equivalent length is equal to 3 meters. Okay, now our concern is to compute for the moment of inertia with respect to axis, to x-axis. But in this case, we know that we have to identify first the neutral axis or the location of the neutral axis. So that means we can say that it is somewhere here, but first we are going to compute what is the location of this. So let us say from here, okay, this is neutral axis going here. We can assume as y bar, or the location of the neutral axis from the bottom, and we can divide this as number area 1, and this one is for area 2. So from here we can compute first what is area 1. Area 1, this is the area of the rectangle, 240 times 20. This will give us 4,800 square millimeters. Area 2, this one, so this is 20 and 100. So you have 20 times 100. So you have 2,000 square millimeters. In other words, your total area is just equal to 4,800, and 2,000 is 6,800 square millimeters. Okay, so let us now uh, locate where the neutral axis is. Okay, so let us copy this one. Let us copy this drawing. Can copy it to the next page. Okay, so we already have the total area been computed, so we can use this formula, the Verignon formula, the area total, and then multiply the centroid coming from the bottom, then area 1, and then y1, plus area 2, and then y2. Okay. So where is our y1? Okay, so this one, our y1 is from the center, this one coming here. This should be our y1. Okay, so what is our y1? If you have here This is 120, this is 10, so meaning this is just 110. And our y2 is from here, from the center of that area 2. If that is 100, meaning y2 here is equal to 50. Okay, so we can substitute 6,800 y bar. We calculated already earlier. A1 is 4,800. Y1 is 110 plus area 2, which is 2,000, and then 50, this one. Okay, so we can simplify. This is 6,800 y bar. This one will become 628,000. Use your calculator. So y bar here is just 628,000 divided by 6,800. So meaning y bar is 92.35 millimeters. So meaning from here it's 92.35. Okay, that's y bar. This is 92.35. Now, in the moment of inertia, since the moment of inertia of this rectangle is here, we're going to transfer it here. Okay, so we need the formula. Moment of inertia, this is the neutral axis. Okay, at x, new x, so we can say x bar is just equal to the moment of inertia, area, and then that d squared. So for example, what is that d? So we consider first for, let's say for 1, what is our d1? From here going to here, what is our d1? Okay, d1 is just, see distance over here is 110, you deduct minus, you subtract 92.35, will have d1. So this is 110 minus 92.35, so will give us 17.65 millimeters. How about d2? Where's our d2? D2 is from here going here. This is our d2. Okay, so what is our d2? See, this y bar, you deduct 50, will give you d2. So that y bar is 92.35. You subtract 40, will give us 40. No, it's 50. Okay, this is 50. This is 50. This one. 42.35 millimeters. Okay, so now transferring it, we can compute. Okay, the moment of inertia. Okay, at the new x location, the area of the rectangle is just BD cube over 12 plus AD squared. Okay, for number 1, okay, this area 1, B is 240, and then you have D is 20, this one, cube over 12. Area A1 is given to be 4,800. 4,800. D is, okay, D1. First is D1. You have 17.65 squared. This is just, this one is just for number 1, area 1. For number 2, should we say plus, B is 20, D is 100, cube over 12 plus area 2, which is 2000. We calculated already earlier. D2 is this one, 42.35 squared. Okay, So I could be calculated. This is just equal actually to 6,909,019.67 okay, this is millimeter to the power 4. Okay, if you calculate this one by one, okay, you can have this value. Okay, so we can convert. We know that 1 meter is 1000 millimeters. Okay, multiply it to the power 4 so that we can cancel this millimeter. Thus, we can have 6.91 times 10 to the negative 6, and this one becomes metal to the power 4. Okay, now we get the moment of inertia. Earlier we have in this direction. Now if we are going to get the moment of inertia at the y-axis, okay, at the y-axis we can just rotate it so that it will be easier for us to understand. Okay, I could do like this. I could just do like this. Earlier, okay, as I say, it's supposed to be like this, okay? Now, since you are interested in this y-axis, so let us just rotate it in this way so that it will be easier for us to understand, okay? So you can do like that. Okay, now the moment of inertia with this y-axis. If you see, number one, there's no need to transfer, okay? Because the moment of inertia of this one rectangle is coinciding with the centroid of this rectangle is coinciding with the centroid of the whole section. Okay, so on moment of inertia with y bar with y is equal to bd cube over 12. Okay, moment of inertia of rectangle is bd cube over 12. This is rectangle and this is also rectangle. So first here, b is 20, d is 240 cube over 12. There's no need of transfer. As I said, there's no need of transfer because the centroid of the rectangle of that area 1 is exactly the same with the centroid of the whole section. Okay, plus this one, b is 100, d is 20 cube over 12. So iy here, okay, moment of inertia with respect to y, neutral axis to y. Calculating this one, we'll have 23, 106, 66.67 millimeter to the power 4. If we're going to convert this one to meter, we divide by 1000 to the power of 4. In other words, we can have here 2.31 times 10 negative 5, okay, meter. Earlier, our calculation is, yeah, our calculation is this one, okay, but this one 6.95, this is neutral axis with x, okay, which is it is here, okay, this is the x prime if we're going to rotate. Okay, so this is negative 6, meaning this one is smaller compared to here, so we're going to use this at x prime. Okay, we're going to use this one for our Euler formula. Okay, so P is equal to pi squared EI all over LE. Okay, we substitute pi squared, and then from the problem it's given to be 200 gigapascal, so I'm going to use times 10 to the power of 6 to make it kilopascal. Kilopascal or kilonewton square meter. Okay, kilopascal is equal to kilonewton square meter. Okay, and then you have here 6.91, the I that we have calculated, times 10 to the negative 6 meter to the power 4. So, so we see here that we are consistent with unit meter. And then our LE, we calculated earlier, or we identified LA earlier, 3 meters squared. So here meter squared, meter squared, meter squared, our answer will be in kilonewton. Okay, so calculating, uh, let's calculate using the calculator. This is 1513.34 kilonewton. This is our P. Okay, again, let us go back to the question. This is the crippling load for the column. Okay, if you will be asked to get the safe load, so you still have to divide by the factor of safety. But in this case, there's no factor of safety given since the crippling load is the one being asked in this problem. So that's all for today, and thank you, and share this video. Follow me as well.